Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hey, what's up everybody? Welcome to the best chemistry live stream on this or any planet. I'm just kidding, I don't know if that's true. I spend a lot of time looking up other people's chemistry stuff. Perhaps I should. I don't know. Anyway, welcome to the live stream. It is a great night to discuss electrochemistry. At least that is my opinion, and I hope you share the same opinion with me, because we are going to get right into this content. Without further ado, I present to you Electrochemistry, Volume 6. As always, I really appreciate your feedback, so please feel free to leave your feedback in the form of a comment if you're watching this later after the fact, this video, or in the form of a message in the chat if you are watching this live. And also, if you're watching live, please feel free to call into the show using Discord. There's a link right down there in the description if you like. I would love the opportunity to have a face-to-face discussion with you. I think that'd be pretty cool. All right, everyone. Let's go ahead and start things off as we normally do by reviewing the content from the previous live stream. Of course, the previous stream was Electrochemistry Volume 5, and I just want to provide the following caution, a word of caution, which is the stuff that we're going to talk about tonight in Volume 6 relies heavily on understanding the concepts that were covered in Volume 5. And so to that end, I say I don't really recommend watching this stream, this video, Volume 6, until you have watched Volume 5. Now, if you're watching this live, please don't click away, because I like to have live viewers. But yeah, so if you haven't watched Volume 5 yet, I recommend watching Volume 5 before you watch Volume 6. So with that little disclaimer out of the way, let's talk about the Volume 5 material briefly. So in Volume 5 was all about understanding the relationships between cell potential, right? Potential difference in a voltaic cell potential. The relationships between cell potential and a couple other properties that we've looked at in previous live stream series, which are the change in Gibbs free energy, delta G, and the equilibrium constant, K, right? Now, we already understand, or at least if you were watching my thermodynamics content from the previous live stream series, right, we already sort of understood the relationship between delta G and K. It was covered, I believe, in Volume 6 of my thermodynamics live streams playlist, right? And that equation is as follows, where we have standard delta G equals minus RT ln K. R, of course, is the gas constant. T is the absolute temperature. K is the equilibrium constant, right? And so we were able to use that relationship to derive equations associated with the relationship between delta G and cell potential, and equilibrium constant and cell potential. So Volume 5 was like a very derivation-heavy stream, right? We did a lot of derivations, and I'm wondering if I can put a poll up right now. Well, I guess it wouldn't be worth it because there's only a couple of people in here watching right now. But I want to know about the people who are watching live. I want to know, put a 1 in the chat if you are actually interested in deriving equations. You want to understand why the equations work the way they do. And put a 2 in the chat if you don't really care about derivations and you just want to skip to the formula so that you can use it to get the right answer on your exam. Right? 1, you actually care about derivations. You want to understand the origin and the meaning behind the equation. Or 2, you don't really care. You just want to see the equation so that you can use it to solve a chemistry problem. I mean, there's really no wrong answer to that, but I would like to know kind of where you guys are at. I guess it doesn't really make a whole lot of difference, because I'm going to do the derivations either way, because I myself personally am somebody who was interested in understanding why these equations, why these relationships work the way they do. But that's just me. So that's kind of how I lecture. That's how I teach, right? All right. So we started things by looking at the relationship between cell potential, standard cell potential, and standard change in Gibbs free energy. And we were able to derive this equation over here, in which we have standard change in Gibbs free energy is equal to minus N times F times the standard cell potential, right? where N is the number of moles of electrons in the balanced chemical equation of the redox reaction, and F is something called Faraday's constant, which represents the charge of 1 mole of electrons, which comes out to be 96,485 coulombs for a mole of electrons, right? So that's the relationship between standard Gibbs free energy change and standard cell potential. There really should be a degree sign up here. I forgot to put it in. Anyway, so we understand that equation. We use that equation in order to solve a problem. So we did a couple of examples in volume 5. And then switching gears, we also looked at the relationship between standard cell potential and the equilibrium constant. And this over here is the equation that we derived that denotes that relationship, right? Where we have standard cell potential is equal to 0.0592 volts over N times the decimal logarithm, the base 10 logarithm of the equilibrium constant, where N, of course, is the number of moles of electrons in the balanced chemical equation of the redox reaction, right? Got a couple messages in the chat. Roberto says, "Hey, Ben, just watching your channel update video." He says, "I think it's cool to know where equations come from." Great. Yeah, definitely. I would agree with that. Unfortunately, I don't think everybody agrees with that. I think probably the majority of students don't really care about where the equations come from. They just want to use them and get an A on their test and then hopefully never think about the stuff again. But I don't roll that way. That's just not the way it's just not my style, Not what I do. All right, so I think we are ready to move on, right? So what are we going to talk about tonight? Well, we're going to talk about the relationship between cell potential and concentration, right? So we understand that in a voltaic cell, you have electrodes which are immersed in aqueous solutions that have cations in them, positively charged metal ions in those aqueous solutions. So the entire time we've been talking about cell potential, numerically speaking, we've been talking about standard cell potential, which I will remind you that standard cell potential means the cell potential such that every reactant and product is in its standard condition. And the standard condition for an aqueous solution is a concentration of exactly 1 molar, right? So the first example, the very, very first example of a voltaic cell that we looked at way back in like volume 2 or something, right, was the zinc and copper electrode, in which in the anode, zinc is oxidized and in the cathode, copper ions are reduced to copper, right? And if we had that voltaic cell, right, and the concentrations of copper ion and zinc ion in that cell were both 1 molar, we could quite easily calculate what the cell potential of that voltaic cell would be, right? We could look up those tabulated values of the standard electrode potentials for our anode and our cathode, right? And we can use the formula for standard cell potential along with those tabulated values of standard electrode potentials to calculate the standard cell potential. In the case of the zinc copper electrode, that comes out to be positive 1.10 volts. Everybody still with me? So when it's 1 molar, when everything is 1 molar, we can calculate it pretty easily. But what if we had the same voltaic cell, in other words, the same 2 half reactions occurring within the half cells of that voltaic cell, but what if the concentrations were not 1 molar? What if these were non-standard concentration? So for instance, what if we had the same reaction, right? The zinc and copper voltaic cell, right? And what if the concentration of copper ion in the cathode was 5 molar? And what if the concentration of zinc ion was 0.1 molar in the anode? How would we calculate the cell potential associated with such a voltaic cell? That's what we're going to talk about tonight. So tonight we are going to derive an equation that allows us to calculate cell potential when we have non-standard concentration, when the concentrations of the aqueous ions are not 1 molar, right? And so before we start deriving that equation, I just want to see if we can get like an intuitive understanding of what we think is going to happen in this case down here, right? So in this case down here, we have a reactant with a concentration that is higher than standard concentration, and we also have a product where we have a concentration that is lower than the standard concentration, right? 5 molar is higher than 1 molar, 0.1 molar is lower than 1 molar, right? And so what effect do you think that would have? Without picking up your calculator, right? If you just think intuitively about this, right? What do we know? Well, hopefully, we all remember from when we were studying chemical equilibrium of a little concept called Le Chatelier's principle. Does that ring a bell? I hope it does. Should. So Le Chatelier's principle, what does that tell us? Right? It tells us that when a reaction at equilibrium is disturbed, the reaction will respond in a way that opposes or counteracts the disturbance, right? So if we apply Le Chatelier's principle, right, to concentrations that differ from standard concentrations within a voltaic cell, how can we predict what effect these concentrations will have when compared to our standard cell potential? Well, if you look at the concentration of copper in this particular reaction, it's higher than standard, right? That is essentially increasing the amount of a reactant. And according to Le Chatelier's principle, when you increase the amount of a reactant, the reaction is going to respond the opposite way. It's going to try to decrease the concentration of that reactant. How does it decrease the concentration of that reactant? Well, it reacts in the forward direction to get rid of that added reactant that you put in there, right? And so based on the fact that 5 molar is larger than 1 molar in the case of this reactant, we would expect the reaction to have a greater tendency to proceed in the forward direction than under standard conditions, right? And then if you look over here at the product, right, the zinc ion, its concentration is less than standard, right? And so that basically has the effect of removing a product, decreasing the concentration of a product. And if you decrease the concentration of a product, according to Le Chatelier's principle, the reaction is going to respond in a way that increases the concentration of that product, right? Which is to go in the forward direction, right? So because we have a reactant whose concentration is higher than standard and a product whose concentration is lower than standard conditions, we would expect this redox reaction to proceed more or to have a greater tendency to proceed in the forward direction than it would under standard conditions. And in terms of the cell potential, what does that mean? That means that we would expect the value of cell potential for this non-standard reaction to be higher, have a greater tendency to occur than the value of cell potential for this redox reaction under standard conditions. Okay, so again, this is just kind of something you can intuitively think about, right? I really, really want to teach you guys like how to think about this. I don't want you to just memorize a bunch of stuff and just regurgitate it when it comes test time, right? I want you guys to think like a chemist. And I promise you, it will serve you well in your homework and exams or whatever else you might have. All right, so let's derive the equation that shows us the relationship between cell potential and concentration of those aqueous cations, shall we? To do that, I'm going to take you guys over to the whiteboard, and we are going to start with an equation that we covered when we talked about thermodynamics. And the equation describes the relationship between non-standard change in Gibbs free energy, non-standard delta G, the relationship between that and concentration, right? And that equation, I think it was covered in volume 6 of my thermochemistry live streams playlist. That equation looks like this. Let me see if I can find my cursor here. Oh, I can't find it. That's not what I want to do. Okay, so that equation looks kind of like this. Do that. Okay. So we have delta G under non-standard conditions is equal to the standard delta G plus the product of R and T and the natural log of Q, right? So let's talk about what all these things are. Again, this is what we're starting with, and this is something that we looked at, that we derived back in the day when we were talking about thermodynamics volume 6. I'm pretty sure that was the episode. So, of course, delta G, that's your non-standard change in Gibbs free energy. And the reason why delta G is so important is because delta G is the criterion for spontaneity, right? Cell potential, you can think of cell potential as just like a manifestation of delta G. So of course they're related somehow, and this is the chance that we have to sort of unpack the relationship, right? So non-standard delta G is equal to standard delta G plus RT ln Q. So R, right, that's the gas constant. That has a value of 0.314, and that's joules per mole per Kelvin, right? T, that's simply the temperature, and that's in kelvins. Under standard conditions, it's usually 25 degrees Celsius or 298.15 kelvins, right? And then Q, what's Q? Q is called the reaction quotient. Reaction quotient. Right? And this is a point in your education where it might be helpful to know a lot about chemical equilibrium, because chemical equilibrium was the topic in which we introduced what the reaction quotient is, right? Reaction quotient, it has the same expression for the equilibrium constant, which is the concentrations of your products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. The same expression as the equilibrium constant, just with the understanding that it's taking place. Oh, thank you so much, Roberto, for the $3, man. Next time, I want you to attach a chat message to that so we can all hear it and read it on stream. Thank you, bro. Appreciate it. Right, so the reaction quotient, it's the same expression as the equilibrium constant with the understanding that the reaction is currently not at equilibrium, right? So we have delta G equals standard delta G plus RT times ln Q, right? Now, another thing that we learned in last live stream, right, because we derived the relationship between delta G and standard cell potential, right? And I'll go ahead and write that one back on the board. So it's delta G standard is equal to minus NF times standard cell potential, right? Where N is the number of moles of electrons in the balanced chemical equation of the redox reaction. F is Faraday's constant, 96,485 coulombs per mole of electrons. And of course, E cell, that's the standard cell potential, right? And so what we're going to do is we're going to use this equation here in green, and wherever we see delta G, we're going to substitute minus NF E cell, right? And so if we do that, then our equation is going to break down like this, where we have minus NF times the non-standard cell potential equal to minus NF times the standard cell potential plus RT ln, right? All we've done here is just substituted wherever we see delta G, we put in minus NF E cell. Rohan is asking, is this the derivation? Yes, this is where we are deriving the relationship between cell potential and concentration. Okay, so we have this equation right here. This is where we're at so far. Now, what I'm going to do is I'm going to take this equation and I'm going to basically divide the whole thing, right? Divide the whole thing by minus NF in an attempt to clean this equation up a little bit, just make it a little nicer, a little prettier to look at. So if I take this whole equation and I divide every term in here by minus NF, well, again, it's going to simplify things. It's going to clean it up a little bit, right? We're going to end up with non-standard cell potential equal to standard cell potential minus RT divided by NF times the natural log of Q, right? And again, all I did to get here was just take this whole equation divided by minus NF, okay? Everybody still with me? I hope so, because we're going to continue. All right. So there's a couple of things more that we can do with this equation here to sort of clean it up a little bit, right? Because if we think about it, right, R, that's a constant. F, Faraday's constant, that's also a constant. And usually, for the most part, these things are done at 25 degrees Celsius. So for our intents and purposes here in general chemistry, we can assume that T is also constant at 25 degrees Celsius, right? Most of these reactions are done at room temperature, and fluctuations from room temperature don't really have much of an effect on cell potential. Small fluctuations don't anyway, right? And so since R, T, and F are all constants, right? And also another relationship that's important to understand is that the natural log of Q is the same as the product of 2.303 gram, or sorry, 2.303 times the decimal logarithm of Q, right? And this relationship here is what's going to help the following equation that we're going to put up here make a little bit more sense. So if that seems a little confusing right now, just bear with me, right? And so what we're going to do is we're just going to rewrite this this equation in a way that sort of cleans it up and makes it easier to apply in the event of a calculation. And the equation that we end up with is the following, where we have the non-standard cell potential equals the standard cell potential minus 0.0392. Sorry, I messed that up already. 0.0592 over n times the decimal logarithm, the base 10 logarithm of Q, right? So this is the equation that we just derived. This is the equation that describes the relationship between cell potential and concentration. And this equation is so important that it has a name. This equation is so important that it has a name. And as you probably can tell, I don't know why my stuff just appeared off screen there. Let me center it back again. All right, so the name of this equation that we just derived, I'll display as much of it on the board as I can. Let's see if I can display the entire derivation, so I don't leave anything out. Okay, so finally, the name of this equation, it's called the Nernst equation. N-E-R-N-S-T equation, right? That is this thing right here. So it's so important that it's got a name. Kaylee839 says, hello. Hello, Kaylee. It is nice to see you again. I think the last time I heard from you, you were expecting, which is really, really, really exciting. I hope I'm not wrong. That's a pretty bold thing to be wrong about. But it's nice to see you again. And thank you for hopping in here. Rohan says, how did you get the 0.0592 again? Right, so you get that, right, by taking R and T, dividing it by F, right? So if R is 8.314 joules per mole times Kelvin, T is 298.15 Kelvin, F is 96,485 coulombs per mole of electrons, and then natural log of Q is the same thing as 2.303 times the decimal log of Q. If you multiply all those things together and divide all those things and just kind of include all of those constants into one constant, then you end up with that minus 0.0592 over n times the log of the reaction quotient. Of course, n is the number of moles of electrons in the balanced chemical equation of the redox reaction. I hope that answers your question. Yeah, it looks like Rohan sort of helped with that one. Thank you, Rohan. Appreciate it, man. All right. So now that we have derived this equation, we understand the origin of this equation and why it works the way it does. Now, I think we're ready to apply this equation in pursuit of solving a problem. So bear with me for a moment. I'm going to erase everything here, and I'm going to paste the problem on the board. By the way, if this stream is valuable to you, then I would wholeheartedly appreciate you leaving a thumbs up on it. That goes a long way to help with discoverability within the increasingly shitty YouTube algorithm. And also, if you would like to support the stream monetarily, as Roberto did a few moments ago, there's a couple of ways to do that. You can do it via Streamlabs. There's a link down in the description that says support the stream. You can donate via PayPal through Streamlabs. You can put a text-to-speech donation that appears on the screen. It's a lot of fun, very interactive way to support the channel. And then you can also send things like super chats, super stickers, which are very, very easy, although YouTube takes a bigger cut and blah, blah, blah. Okay. So that's how you support the stream if you want to. Let me go ahead and copy, paste the problem here into the whiteboard so we can continue. All right, so there it is. I wish it would appear bigger on my screen by default. It always appears so small and I have to resize it. There's Microsoft Whiteboard for you. Oh yeah, you guys are both named Rohan. That just dawned on me. Nice. All right. So let's get to the problem so we can get to the solution, folks. What do you say? I say yes. Let's go. Let's go. All right. So the problem says voltaic cell is based on the two half reactions below. So these two half reactions are shown here. This is the oxidation half reaction up here, where you have magnesium undergoing oxidation to form magnesium ion. and it says it has a concentration of 4.00 molar, and there's 6 electrons that are released from that half reaction. And then our reduction half reaction involves the reduction of ferric ion, the reduction of Fe3 plus ion, with a concentration of 0.030 molar and 6 electrons to produce 2 moles of iron, right? So these are our 2 half reactions. And the question simply asks us to calculate the standard, or not the standard, the cell potential. This is non-standard because the concentrations are not 1 molar, right? Calculate the cell potential at 25 degrees Celsius, right? So, as you have probably already figured out, we're going to be using the equation that we just derived, right? Which is that standard, non-standard cell potential. I don't know why I keep calling it standard cell potential, is equal to the standard cell potential minus 0.0592 over n times decimal logarithm of Q, the reaction quotient. Right? So there's kind of a lot to unpack with this one, right? We have to do a lot of work to solve this, right? N, that's pretty straightforward. That's 6 electrons. But it's going to take us some work to calculate the standard cell potential and to calculate Q. And then once we calculated standard cell potential and Q, we can plug those back into this equation, and that'll solve the problem for us. So let's start it off by calculating the standard cell potential. How do we do that? Right? How do we do that? Well, we're going to use the formula for calculating standard cell potential using tabulated standard electrode potentials. There it is. Almost forgot it there for a second. So to calculate the standard cell potential, it's going to be the standard electrode potential of your cathode. That's where reduction occurs, minus the standard cell potential of your anode, where oxidation occurs, right? And so we are at the point where we need to look up the standard electrode potentials in our table of standard electrode potentials so that we can insert them into this formula to get us the standard cell potential, right? So let's go ahead and do that, right? So lucky me, I have that table already set up here. So if we remember, I really should display this stuff on the board as I'm using it. And also, look at this. My webcam is not even showing. There it is. Yeah, I'm still kind of a newbie at streaming, folks, even though I've been doing this for like over a year. I'm still super like inexperienced and green with all this stuff. All right, so if we remember what our electrodes are, right? So in our cathode, right, the reduction reaction is the reduction of Fe3 plus. So let's see if we can find the reduction of Fe3 plus anywhere in this table, and we can locate its standard electrode potential. So it's the reduction of Fe3 plus to just plain old iron. And I think I found it right here. I don't know if you can see my mouse cursor. Yep, this is it right up here. So this is for our cathode. So this has a value of minus 0.036 volts. Minus 0.036 volts, right? So if we go back into the whiteboard, over here where it says E cathode, that's going to be minus 0.036 volts, right? And then we're going to subtract from that the standard electrode potential that occurring in our anode, which is the oxidation or the reverse of the reduction of magnesium ion. You can see here that we're having magnesium being oxidized into magnesium ion. So when we look it up in the table, we're going to look up the reduction of magnesium ion into just plain old magnesium. So let's go back to our table of standard electrode potentials, see if we can find the reduction of magnesium ion. It looks like I found it down here. You can see there's my mouse cursor. So reduction of magnesium ion is right here. That comes in with a value of minus 2.37 volts. Minus 2.37 volts. So we're going to go back to the whiteboard so we can fill that in. So it's minus negative 2.37 volts, right? So if we plug that into our calculators, which I suggest you all do, negative 0.036 minus negative 2.37 what value are you going to get for our standard cell potential for this redox reaction? I got a value of positive 2.334 volts. 2.334 volts. That is our value for our standard cell potential. Rohan Sanji says the signs are confusing. Yeah, I know they can be. It's important to understand that, like, when you subtract a negative, that has the same effect as adding a positive. So it's very, very important that you have like good handwriting and you're keeping up with that. But yeah, I know it can be a little confusing. Okay, so we have just successfully calculated the standard cell potential, right? That's the first sort of hard part of this problem, right? Bear with me. I'm just going to grab the thing right here and just move it over there. Okay. Rohan says, isn't E cell E reduction plus E oxidation? Yeah, you can calculate it that way. So there's a couple ways to think about it. You can think about it as like E reduction plus E oxidation, and then for E oxidation, you understand that it's the negative of E reduction for that given half reaction. But that's one way to think about it. That considers the standard cell potential as like a sum, when in reality, cell potential is a difference. It's the difference in potential energy across the two electrodes. And so the formula where you have E cathode minus E anode, I think that's a better way to do it. Rohan Kumar says, my book has a quite different value for the E cell value of the reduction of iron ion to just solid iron. Okay. Yeah, I'm not sure why we're getting different things based on our textbooks, but let's just go with the one that I have in mind, just so we can move forward with this. Okay, right. So we know, let's get back to the problem. So we know what the standard cell potential is. We know what N is, right? That's the easiest one. That's 6 electrons. Now we need to figure out what Q is, right? We need to figure out what Q is, right? So again, for the reaction quotient, I'll do this in purple color, right? So Q is going to be, again, it's a ratio. It's like a division problem, right? It's going to be the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficient. Now, we can ignore the solid magnesium and the solid iron because we never put pure solids or pure liquids in the expression for a reaction quotient or an equilibrium constant because their concentrations do not change over the course of the reaction. We only include things like gases and things that are aqueous, right? And so we have two species here that are aqueous. We have magnesium ion, which is a product, and we have iron ion, which is a reactant, right? So since magnesium is the aqueous product, we're going to put that up top. So it's going to be a concentration of Mg2+, and we're going to raise that to the power of its coefficient, which is 3. So we're going to cube that, right? Concentration of magnesium ion cubed over concentration of iron ion, Fe3+, and we are going to square that because the coefficient in front of that iron ion, try saying that 3 times fast, iron ion, the coefficient in front of this thing is 2, so we square it, right? So now we can just sort of substitute the values for those concentrations into this equation here, right? So the concentration of the magnesium, that's 4.00 molar, and we're going to cube that. And then for the iron, what is that? That's 0.030 molar, and we are going to square that, right? So again, I would highly encourage you to follow along, take those scientific calculators out, dust them off, and follow along. That's the way to get the most value out of these streams, is if you participate, take an active role in your education, man. Grab it by the, I'm going to be PG here, grab it by the horn. All right, so 4 cubed divided by 0.03 squared. What does that turn out to be? The value that I got, the very large number, is 7.11 times 10 to the 4. 7.11 times 10 to the 4. That is the value of Q, right? Very large number. So just like I did for that standard cell potential, I'm just going to erase everything leading up to Q and just kind of give the value here so I can give myself more than enough space to continue with this, right? We've done all the hard stuff, right? We've calculated standard cell potential. We've calculated Q. And now, whoops, didn't mean to erase that. I have to grab it and bring it over here next to that Q. Now that we have Q and now that we have standard cell potential, and of course we knew N the entire time given by the reaction, now we can insert these things into this equation over here, and that will give us our value for the non-standard cell potential in this voltaic cell. All right, go. So we're going to get that the non-standard cell potential, E cell, is equal to our standard cell potential, which is 2.334 volts, minus 0.0592 over number of electrons in the number of moles of electrons in the balanced chemical equation, which is 6. And we're going to multiply that by the decimal logarithm of Q, which we just determined to be 7.11 times 10 to the 4th, right? So this is a pretty big expression. And I really like the calculator that I have because my calculator, I can easily type this entire expression out into my calculator. If you're interested, the one that I'm using is the TI-30X2S. TI-30X2S. These things are built to last, man. I had this way back when, over a decade ago when I was in college. So these things are great, man. If you buy one of these and you take decent care of it, as long as you're not like throwing it on the tile floor or anything, like it'll last you a good long time. It's been doing great for me. All right, so I should get like a commission every time one of these things is sold now because I just gave the sales pitch for free. All right, so I am kind of stalling while you guys, solve this. I really want somebody watching in here live to give me a number. Don't be afraid if it ends up being wrong, okay? No one's going to laugh at you, and if they do, screw them. I'll get a moderator to boot them out of here if they laugh at you. By the way, if anybody's interested in moderating my streams, let me know. I don't have any mods. I've never needed them because I don't have any trolls or anything like that. But the time may come. The time may come where people start coming in here trying to troll. Rohan says 2.29 volts is what I got. Yeah, the number that I got was 2.29 volts. That is right. Good job, Rohan. I need to start doing like giveaways or something where like if you get the problem right, like I enter your name into a raffle to get like some prize or something. I think those things will work better if I have more people watching, more people participating. But when I see people like participate and give the right answer, like it really, really drives me to like want to give back somehow. But yeah, that is the right answer. 2.29 volts. Very good. Very good. I'm glad at least one person in here is following along. And to the other ones of you who aren't, I'm just happy you're in here watching, man, for real. Okay. So now that we have our answer, right, we could just stop and say, that's great, we got our answer, let's move on. But one thing I want to do is I want to check to see, to make sure that our answer makes sense, right? And so 2.29 volts. How does that compare with our standard cell potential of 2.334 volts? It's less, right? The cell potential for our non-standard condition given by the problem is less than our standard cell potential, right? Should that be the case? Well, if we think about it, again, from a Le Chatelier's principle point of view, right? We have a lower than standard concentration of a reactant. We have a higher than standard concentration of our product. And so, yeah, it makes sense, right? If the concentration of product is high, that's going to drive the reaction in the reverse direction to get rid of that extra product, right? If the concentration of our reactant is low, that's going to also drive the reaction in the reverse direction because it's trying to replenish that concentration of that reactant that was lost. And so everything kind of checks out. It makes sense according to Le Chatelier's principle, and we followed all the steps correctly to get to the answer. So job well done, everybody. We successfully solved this problem. All right, folks. So there's one more thing that I want to talk about briefly. I don't want to do any more any problems on it or anything like that, but it's just something that I think is kind of cool. Something that I think is kind of cool. So I think it's worthwhile to talk about it. And that is something called concentration cells. So we're going to talk about that briefly, and then that'll be kind of it for tonight's stream. So we're going to talk about concentration cells. So what is a concentration cell? Well, the image on your screen here is a diagram of one example of a concentration cell, right? It looks fairly similar to the voltaic cells that we've seen in the past, right? You've got an anode written on the left. You've got a cathode written on the right. We know what direction electrons will flow in. They'll flow from the anode to the cathode, right? But one thing that's interesting about this cell is our anode and our cathode are both made of zinc. They're the same material. And if you look at the solution of our anode and the solution of our cathode, they are both zinc ion. That's kind of interesting. So how do you get electron flow if your anode and your cathode are identical material and the aqueous solutions are the same thing, right? Well, in a concentration cell, the flow of electrons is driven by differences in concentration, right? Because we just established that cell potential not only depends on the identity of the electrode, but it also depends on the concentration of the aqueous solution in which that electrode is immersed, right? And so if you have a dilute solution of zinc ion, in this case, in your anode, right, and you have a concentrated solution of zinc ion in your cathode, well, what's that going to do? That's going to drive the flow of electrons, right? That's going to drive the flow of electrons. The equations for these two half reactions are shown here, right? And so if you have a dilute zinc solution, that basically means like you have a very low non-standard amount of your product of this half reaction, so that drives that reaction forward, right? And then in the reduction half reaction, it's just the reverse of the oxidation half reaction. You have a very, very concentrated, right, higher than standard concentration of zinc ion in your solution here of your cathode, right? And that has the effect of having a high reactant concentration, which drives this reaction forward. So you have sort of two things going that drive the reaction forward. And I just want to say that if you have a concentration cell, eventually, right? So eventually the concentration of zinc in your dilute solution will sort of increase, right? As this zinc continues to go on, try that one again. As this zinc in the anode continues to undergo oxidation, it'll produce more zinc ions. So the concentration of your dilute solution is going to go up in the anode. And then in your cathode, the concentration of this zinc ion solution is going to go down, right? As the zinc ion continues to undergo reduction in your cathode. So eventually it will sort of like equilibrate, and the concentrations of these solutions will be the same. And at that point, there will be no flow of electrons. The cell potential at that point will be zero because you have two completely identical half cells connected together. All right, guys. So that is going to do it for me tonight. Thank you all very much for watching. Big thank you to those who participated, and a super big thank you to the one of you that actually donated to the stream. I really, really appreciate all the support that I get, whether it's being here, participating in the chat, leaving a like on the stream, monetarily donating if you have the means. I appreciate all of it. Thank you guys so much for everything. I hope, sincerely hope, that this stream was valuable to you. And I also would hope that you come back and see me next week. So right now it's March 27th. So that means next Sunday is going to be April 3rd. I stream every Sunday, 9 o'clock p.m. Eastern time here in the US. So I hope to see you then. Love you guys, and I'll talk to you soon.